Hey everyone, tonight we're exploring one of the most profound and mysterious discoveries in modern cosmology, the accelerating expansion of our universe. Before we settle in for this cosmic journey, take a moment to like this if you enjoy these deep space explorations, and let me know in the comments where you're listening from and what time it is for you. I always find it fascinating how our global community gathers to contemplate the cosmos together, united by wonder across all time zones. Now get comfortable, dim those lights, and let your breathing slow. Tonight, we're not chasing dramatic cosmic collisions or explosive stellar deaths. Instead, we're going to examine something much more profound and peaceful, the gentle, inexorable stretching of space-time itself, driven by the mysterious force we called arc energy. Let's begin our gentle journey into this infinite mystery. Imagine, if you will, the universe as a vast ocean of space and time, where galaxies drift like distant islands in an ever-expanding sea. But this is no ordinary expansion, it's accelerating, growing faster with each passing moment. This discovery, made just decades ago, fundamentally changed our understanding of cosmic destiny and revealed that empty space itself carries a hidden energy, gently but persistently pushing the fabric of reality apart. Tonight, we'll explore how astronomers first glimpsed this acceleration through the dimming light of distant stellar explosions, how this mysterious dark energy comprises nearly 70% of everything that exists, and what this means for the ultimate fate of our cosmos. We'll contemplate how space itself grows, carrying galaxies ever farther apart in a dance of eternal separation that will continue long after the last stars have burned out. This is a journey through deep time and vast scales, where we'll find peace in the universe's patient unfolding and discover profound beauty in the cosmic processes that shape our reality. So settle back, let your mind expand with the cosmos, and prepare to drift through the gentle mysteries of our accelerating universe. In the vast tapestry of cosmic discovery, few revelations have been as profound and quietly revolutionary as the realization that our universe is not merely expanding, but accelerating in its expansion with each passing moment. This gentle yet inexorable process, driven by the mysterious force we call dark energy, represents one of the most beautiful and contemplative mysteries in all of modern astronomy. Picture, if you will, the patient work of astronomers in the closing decades of the 20th century, their telescopes strained on the most distant reaches of observable space. They were searching for stellar explosions so brilliant and consistent that they could serve as cosmic lighthouses, illuminating the deepest questions about our universe's fate. These were IPA supernova, stellar deaths so uniform in their brightness that they became the universe's most reliable standard candles, each one a beacon capable of revealing the expansion history of space itself. The story begins with teams of dedicated researchers, led by scientists whose names would eventually be etched in the annals of cosmic discovery. Saul Perlmutter of the Supernova Cosmology Project and Brian Schmidt and Adam Rees of the Heise Supernova Search Team embarked on a methodical quest to measure the universe's expansion rate across vast stretches of cosmic time. Their approach was elegantly simple in concept, yet monumentally challenging in execution. By observing supernova at various distances, they could trace how the expansion of space had changed over billions of years. These stellar explosions, occurring when white dwarf stars accumulate matter from companion stars until they reach a critical mass, always release the same tremendous amount of energy. This consistency makes them perfect cosmic yardsticks, allowing astronomers to determine precise distances to galaxies billions of light years away. As these researchers painstakingly collected data from dozens of distant supernova, they expected to find evidence that the universe's expansion was gradually slowing down, pulled back by the gravitational attraction of all the matter it contained. But the universe, in its infinite capacity for surprise, had other plans. As the data accumulated through years of careful observation, a puzzling pattern emerged. The distant supernova appeared dimmer than expected, suggesting they were farther away than calculations predicted. This distance was subtle, requiring the most sophisticated instruments and analysis techniques to detect, but its implications were staggering. If these stellar explosions were indeed farther away than anticipated, it could only mean one thing: the expansion of space itself was accelerating, carrying these distant galaxies away from us at an ever-increasing rate. The moment of realization must have been both exhilarating and deeply humbling for these cosmic explorers. Here was evidence that some unknown force was pushing the very fabric of space-time apart with increasing vigor, a force so pervasive and powerful that it dominated the universe's evolution on the largest scales. This discovery would fundamentally reshape our understanding of cosmic destiny, suggesting that rather than eventually collapsing back upon itself for coasting to a gentle stop, our universe was destined for an eternal expansion, with galaxies growing ever more distant from one another as eons passed. The implications rippled through the scientific community like waves across a cosmic pond. If the universe was accelerating, then something was acting against gravity on cosmic scales, something that comprised roughly 2/3 of all energy in existence, yet remained completely invisible to direct observation. This mysterious component, dubbed dark energy, became the universe's greatest puzzle, a force so fundamental to cosmic evolution that understanding it would require revolutionizing our most basic theories of physics. As we contemplate this gentle revelation, we find ourselves face to face with the profound beauty of cosmic discovery. The universe's acceleration is not a violent or dramatic process, but rather a patient, inexorable stretching of space itself, carrying galaxies apart like leaves floating on the surface of an ever-expanding pond. Each passing moment sees the distances between galaxy clusters grow imperceptibly larger, each second witnessing the universe becoming slightly more spacious, more expansive in its infinite grandeur. This discovery represents more than just a scientific breakthrough. It offers us a new lens through which to view our place in the cosmic order. In a universe that expands with increasing speed, we are reminded of the precious nature of cosmic connections, the fleeting opportunities for galaxies to interact and influence one another before being carried beyond each other's reach by the patient tide of accelerating expansion. In the vast tapestry of cosmic existence, there exists a force so subtle, so pervasive, that it remained hidden from human understanding for billions of years, quietly orchestrating the universe's grandest transformation. This invisible architect of cosmic destiny is what we have come to call dark energy, a mysterious presence that comprises nearly 70% of everything that exists, yet reveals itself only through the gentle, inexorable stretching of space itself. Imagine, if you will, the fabric of reality as an infinite ocean of possibility, where every point in space carries within it a fundamental energy, a quiet vitality that pervades the vacuum itself. This is not the dramatic energy of exploding stars or colliding galaxies, but something far more profound and peaceful, an intrinsic property of existence that manifests as the gentlest of pressures, pushing the universe toward ever greater expansion with the patience of eternity itself. The nature of dark energy presents us with one of the most beautiful paradoxes in all of physics. Unlike the matter we see around us, which tends to clump together under gravity's attractive embrace, dark energy exhibits what we might call an anti-gravitational character, not pulling things together, but rather encouraging them to drift apart. This is not a violent repulsion, but rather a serene and steady influence that operates on the largest scales imaginable, affecting the very geometry of space-time with the quiet persistence of a gentle tide. In the early decades of the 20th century, Albert Einstein, in his profound contemplation of the universe's structure, introduced what he called the cosmological constant, a mathematical term that could provide the universe with a natural tendency toward expansion or contraction. At the time, believing in a static cosmos, Einstein would later call this addition his greatest blunder, yet in the cosmic irony that so often characterizes scientific discovery, this discarded concept would prove to be one of his most prescient insights. The cosmological constant, represented by the Greek letter lambda, embodies the simplest possible explanation, for vacuum of space itself possesses an inherent energy density, a fundamental property as basic as the speed of light or the charge of an electron. In this view, empty space is not truly empty, but filled with a subtle energy that creates a gentle outward pressure, causing the universe to expand at an ever-accelerating rate. From the perspective of quantum field theory, this vacuum energy emerges from the ceaseless dance of virtual particles that flicker in undoubt of existence throughout the cosmos. These ephemeral entities, borrowing energy from the quantum vacuum for the briefest of moments before returning it, create a background hum of activity that permeates all of space. The cumulative effect of these quantum fluctuations should, according to our current understanding, contribute to the energy density of the vacuum itself. Yet here we encounter one of the most profound mysteries in all of physics, the cosmological constant problem. When physicists attempt to calculate the expected energy density of the quantum vacuum, they arrive at a number that is not merely large, but incomprehensibly vast, some 120 orders of magnitude greater than what we observe. This represents perhaps the most dramatic failure of theoretical prediction in the history of science, suggesting that our understanding of the vacuum's true nature remains tantalizingly incomplete. Alternative theories propose that dark energy might not be constant at all, but rather a dynamic field that evolves over cosmic time. These models, often called quintessence after the fifth element of ancient philosophy, imagine dark energy as a slowly rolling scalar field that permeates the universe, its strength and character changing as the cosmos ages. Like a vast, cosmic weather system operating on temescals of billions of years, this field would create the observed acceleration through its gentle evolution across the expanding universe. The equation of state parameter, denoted by the letter W, provides astronomers with a crucial tool for distinguishing between these various possibilities. For Einstein's cosmological constant, W equals exactly -1, representing a perfectly uniform energy density that remains constant as space expands. For quintessence models, W might vary slowly over time, potentially crossing this critical threshold and revealing the dynamic nature of dark energy through precise observations of cosmic acceleration. As we peer deeper into the cosmic mystery, we find that dark energy's influence extends far beyond simple expansion. It affects the formation of cosmic structure, the evolution of galaxy clusters, and even the propagation of light across the universe. The gentle pressure of dark energy works against gravity's tendency to pull matter together, creating a cosmic balance that has shaped the universe we observe today. The profound implications of dark energy's existence extend into the very foundations of physics itself. If confirmed as a fundamental property of space-time, it would represent a new kind of field, unlike anything in our current theories. This invisible ocean of energy challenges our understanding of gravity, quantum mechanics, and the very nature of space and time, inviting us to contemplate possibilities that stretch the boundaries of human imagination. In the quiet moments of cosmic contemplation, we might find a strange comfort in dark energy's gentle persistence. Like a cosmic breath that slowly expands the universe with each passing moment, it operates with a patience that transcends human temescals, reminding us that the cosmos unfolds according to its own serene rhythm, indifferent to our hurried concerns, yet somehow providing the perfect conditions for our existence and wonder. The fabric of space-time itself breathes with a gentle, eternal rhythm, expanding ever so slowly yet inexorably, carrying within its very essence the profound mystery of cosmic acceleration. To understand this expansion is to glimpse the deepest nature of reality itself. where space and time are not merely empty stages upon which cosmic drama unfolds, but active participants in the universe's grand choreography. When we speak of cosmic expansion, we must first release ourselves from the familiar notion of objects moving through space. The galaxies that populate our universe are not racing away from each other, like runner are carried along by the expansion of space-time itself. Imagine, if you will, a vast tapestry being gently stretched in all directions simultaneously. The threads of this cosmic fabric represent the very geometry of space and time, and as they stretch, everything woven into the tapestry moves apart without any force pushing or pulling upon it. This expansion was first glimpsed by Edwin Hubble in the 1920s, when his patient observations revealed that distant galaxies appeared to be receding from us with velocities proportional to their distance. The farther away a galaxy stood in the cosmic deep, the faster it seemed to retreat into the darkness. This relationship, now known as Hubble's law, provided the first concrete evidence that our universe was not static and eternal, but dynamic and evolving. The mathematical description of this expansion emerges from Einstein's field equations of general relativity, specifically through the work of Alexander Friedmann, who derived the equations that govern the evolution of a homogeneous, isotropic universe. These Friedmann equations reveal that the expansion rate, characterized by the Hubble constant, is intimately connected to the total energy density of the universe and the curvature of spacetime itself. As we contemplate this cosmic stretching, we must envision spacetime as a four-dimensional manifold, where the three familiar dimensions of space are interwoven with the dimension of time. The expansion affects only the spatial dimensions, causing distances between distant objects to increase, while leaving the local structure of spacetime relatively unchanged. This is why the atoms in your body, the Earth's orbit around the Sun, and even our entire galaxy remain stable despite the universe's expansion. The gravitational and electromagnetic forces that bind these systems are far stronger than the gentle pull of cosmic expansion at these scales. The expansion of spacetime has profound implications for how we understand cosmic distances and the journey of light across the universe. When we observe a distant galaxy, we are seeing it as it was billions of years ago when the light first began its journey toward us. During this vast span of time, the universe has continued to expand, stretching the very wavelengths of the photons as they travel through space. This stretching manifests as a redshift, where the light from distant galaxies appears shifted toward longer, redder wavelengths. The concept of moving coordinates helps us understand this expansion in a more intuitive way. Imagine a cosmic grid painted onto the fabric of spacetime itself. As the universe expands, this grid stretches uniformly, but objects that are at rest with respect to the expansion remain at fixed positions on the grid. Galaxies, for the most part, are moving with the expansion, carried along by the stretching of space itself, rather than moving through space under their own power. This expansion creates what we call the Hubble sphere, a boundary beyond which objects recede from us faster than the speed of light. This might seem to violate special relativity, but it does not, because these objects are not moving through space faster than light. Rather, the space between us and them is expanding at such a rate that the recession velocity exceeds the speed of light. Light from objects beyond the Hubble sphere can still reach us if it was emitted when these objects were within the sphere, but new light emitted today from beyond this boundary will never reach us. The accelerating expansion driven by dark energy has profound implications for these cosmic horizons. While the Hubble sphere represents the boundary of recession velocities, the event horizon represents the boundary beyond which light emitted today will never reach us, no matter how long we wait. In an accelerating universe, this event horizon is closer than the Hubble sphere, creating a shrinking sphere of cosmic accessibility. As we peer deeper into space and further back in time, we encounter the cosmic microwave background, the afterglow of the Big Bang that fills the entire universe. This ancient light has been stretched by nearly 14 billion years of cosmic expansion, transforming from visible light to microwave radiation. The tiny temperature fluctuations in this background radiation encode the acoustic oscillations that occurred in the primordial plasma, sound waves that were frozen in place when the universe became transparent to light. The patient expansion of space-time has transformed these ancient sound waves into the largest structures we observe in the universe today. The slight overdensities in the primordial plasma, stretched and amplified by billions of years of expansion, became the seeds from which galaxies and galaxy clusters eventually grew. In this way, the expansion of space-time serves as both the canvas and the artist, creating the cosmic web of structure that defines our universe. The measurement of cosmic expansion has become one of the most precise endeavors in modern astronomy. Using a variety of distance indicators, from Cepheid variable stars to Type-A supernova, astronomers have constructed a cosmic distance ladder that extends billions of light years into space. Each rung of this ladder provides a stepping stone to greater distances, allowing us to map the expansion history of the universe with remarkable precision. Yet even as we measure the expansion with ever greater accuracy, the fundamental nature of the space-time that expands remains deeply mysterious. The fabric of reality itself, woven from space and time, continues to stretch in ways that challenge our deepest understanding of physics, carrying within its gentle expansion the seeds of cosmic destiny and the promise of eternal wonder. In the vast theater of cosmic evolution, where galaxies drift like distant islands in an ocean of expanding space-time, we encounter one of the most profound and peaceful contemplations in all of astronomy: the gentle, inexorable process by which cosmic acceleration carries celestial objects beyond the reach of light itself. This is the story of cosmic horizons, of eternal separation, and of the serene isolation that awaits our universe in the deep future. Imagine, if you will, standing on the shore of a vast lake at dawn, watching paper boats drift slowly away from one another as gentle ripples carry them toward distant horizons. This simple image captures something essential about our expanding universe, where dark energy acts as those patient ripples, carrying galaxies ever farther apart with each passing moment. But unlike the boats on our imaginary lake, these cosmic vessels, entire galaxies containing hundreds of billions of stars, are embarking on a journey from which there can be no return. The concept of cosmic horizons emerges naturally from the interplay between expansion and the finite speed of light. As space-time itself stretches, carrying galaxies away from us at ever-increasing velocities, we approach a threshold of profound significance. When a galaxy's recession velocity equals the speed of light, it crosses what astronomers call the Hubble sphere, not because the galaxy is moving through space at light speed, but because the expansion of space itself has carried it to this critical distance. This boundary represents something far more poetic than a mere mathematical construct. It is the edge of eternal accessibility, the point beyond which no signal, no particle of light, no whisper of information can ever reach us again. Galaxies that cross this threshold enter a realm of permanent isolation, their light stretched to wavelengths so long that they fade from our cosmic view, like distant lighthouses disappearing into an infinite fog. The mathematics of this separation unfold with the gentle inevitability of a tide. As dark energy continues its patient work, accelerating the expansion of space, more and more galaxies cross this horizon of no return. Current calculations suggest that in approximately 100 billion years, a time span so vast that it dwarfs the entire history of the universe to date, only the galaxies gravitationally bound to our local group will remain visible to future observers. Consider the profound implications of this cosmic isolation. Future astronomers billions of generations hence will inhabit a universe that appears fundamentally different from our own, where we see thousands of galaxies scattered across the cosmic web, they will observe only the familiar members of our local galactic neighborhood, Andromeda, the Magellanic Clouds, and perhaps a few dozen smaller companions. The rich tapestry of cosmic structure that we study today, the vast galaxy clusters, the cosmic web of dark matter, the distant quasars that illuminate the early universe, all of this will have faded beyond detection, carried away by the patient, inexorable expansion of space. This future cosmic loneliness carries with it a strange beauty. The night sky of that distant epoch will be profoundly peaceful, dominated by the gentle glow of our merged galaxy, for by then, Andromeda and the Milky Way will have completed their slow gravitational dance, creating a single, vast elliptical galaxy that astronomers have already named Milkomeda. This solitary island of stars will drift through an increasingly empty universe, its inhabitants witnessing the slow evolution of stellar populations against the backdrop of an ever-darkening cosmic void. The thermodynamic perspective on this eternal separation reveals another layer of contemplative depth. As galaxies drift beyond our horizon, they carry with them their stores of matter and energy, reducing the total resources available within our observable universe. This gradual depletion represents a fundamental aspect of cosmic evolution, the universe's journey toward maximum entropy, toward a state of perfect thermal equilibrium where no further work can be done. Yet even in this vision of cosmic heat death, we find elements of profound peace. The approach to maximum entropy is not a violent collapse, but a gentle settling, like dust motes slowly coming to rest in still air. Stars will continue to shine for trillions of years, their nuclear fires sustained by the patient fusion of hydrogen into helium. Planetary systems will continue their orbital dances, and life, if it persists, will have eons to contemplate the slow transformation of the cosmos. The observational evidence for this future isolation comes from our careful study of the cosmic microwave background and the distribution of galaxies across space. The integrated Sachs-Wolf effect, a subtle signature in the ancient light of the CMB, provides direct evidence of dark energy's influence on cosmic structure. As photons from the early universe travel through regions of space that are being stretched by dark energy, they experience a slight loss of energy, creating temperature fluctuations that we can measure with exquisite precision. These measurements reveal that dark energy's influence has been growing stronger over cosmic time. In the early universe, when matter and radiation dominated the cosmic energy budget, expansion was actually decelerating. But as the universe grew larger and matter became more dilute, dark energy's constant density began to dominate, initiating the era of accelerated expansion that continues today. The philosophical implications of eternal cosmic separation invite deep contemplation. In a universe where galaxies drift inexorably apart, where the very fabric of space carries celestial objects beyond the reach of light, what does it mean to speak of cosmic unity or universal connection? Perhaps the answer lies not in the physical bridges between distant galaxies, but in the shared laws of physics that govern all cosmic evolution, in the common all-cosmic evolution, in the common origin that links every particle of matter to the primordial fireball of the Big Bang. This cosmic perspective offers a unique form of comfort. In recognizing our universe's journey toward isolation, we gain a deeper appreciation for the present moment, for the rich cosmic environment that surrounds us now. The galaxies we observe tonight, scattered like jewels across the darkness, represent an temporary gathering, a brief cosmic congregation that will slowly disperse over the eons. Their light, traveling across billions of years to reach our eyes, carries with it the story of cosmic evolution, the patient unfolding of structure and complexity in an expanding universe. As we drift towards sleep, carried by the gentle rhythm of cosmic expansion, we can find peace in contemplating this vast, slow transformation. The universe's journey toward isolation is not a tragedy but a natural evolution, as inevitable and beautiful as the changing of seasons or the cycling of tides. In the patient separation of galaxies and the gradual darkening of the cosmic sky, we witness the universe's own form of meditation, a slow, peaceful settling into the deep rest that awaits all things. The cosmic microwave background radiation whispers to us across 13 billion years of cosmic history, carrying within its gentle glow the signatures of our universe's accelerating expansion. This ancient light, stretched and cooled by eons of cosmic growth, serves as a luminous testament to the profound forces that shape our expanding cosmos. As we contemplate this primordial radiance, we find ourselves listening to the universe's first voice, speaking softly of dark energy's patient influence across the vast expanses of space and time. When we gaze upon the cosmic microwave background, we are witnessing the universe as it appeared nearly 380,000 years after the Big Bang, when the cosmos had cooled sufficiently for electrons and protons to combine into neutral hydrogen atoms. This moment, known as recombination, marked the first time that light could travel freely through space without being scattered by free electrons. The photons that emerged from this cosmic dawn have been traveling toward us ever since, their wavelengths gradually stretched by the expanding fabric of space-time itself. The Planck satellite, floating serenely in the cold depths of space, has mapped this ancient light with extraordinary precision, revealing subtle temperature variations that speak to the universe's earliest moments. These tiny fluctuations, measuring mere millionths of a degree, represent the primordial seeds from which all cosmic structure would eventually grow. Yet embedded within these delicate patterns lies evidence of dark energy's influence, written in the language of space and time itself. The baryon and acoustic oscillations frozen within the cosmic microwave background tell a particularly beautiful story of cosmic evolution. In the early universe, sound waves propagated through the hot, dense plasma of photons and matter, creating ripples that would eventually become the scaffolding upon which galaxies and galaxy clusters would form. These acoustic waves traveled at a precisely calculable speed, creating a standard ruler that astronomers can use to measure cosmic distances and the expansion rate of the universe. As dark energy began to dominate the universe's energy budget roughly 5 billion years ago, its influence became imprinted upon the cosmic microwave background through a phenomenon known as the integrated Sachs-Wolf effect. This subtle signature arises when photons from the cosmic microwave background travel through the gravitational fields of large-scale structures that are evolving due to dark energy's influence. The gentle stretching of space-time causes these gravitational wells to become shallower over time, leaving a faint but measurable imprint upon the ancient light. The Condorcan's model of cosmology, built upon observations of the cosmic microwave background, reveals a universe composed of approximately 68% dark energy, 27% dark matter, and only 5% ordinary matter. This remarkable precision represents one of the greatest triumphs of modern observational astronomy, achieved through the patient analysis of countless photons that have traveled across the cosmos to reach our sensitive detectors. The cosmic microwave background also provides crucial constraints on the nature of dark energy itself. By measuring the precise geometry of the universe and the rate of its expansion at different epochs, astronomers can determine whether dark energy behaves like Einstein's cosmological constant, or if it represents something more exotic. The data suggests that dark energy's density remains remarkably constant as the universe expands, neither strengthening nor weakening significantly over cosmic time. As we contemplate these ancient photons, stretched and cooled by billions of years of cosmic expansion, we are reminded of the profound interdependence of all cosmic phenomena. The same dark energy that drives galaxies apart today was already present in the universe's youth, subtly influencing the formation of the very structures we observe around us. This continuity across cosmic time speaks to the fundamental nature of dark energy as an intrinsic property of space-time itself. The cosmic microwave background serves as both a window into the past and a guide to the future, revealing the initial conditions that would eventually lead to our accelerating universe. In its gentle glow, we find not only the story of cosmic beginnings, but also the promise of eternal expansion as dark energy continues its patient work of stretching the fabric of reality ever outward into the infinite depths of space and time. In the vast theater of cosmic time, where billions of years pass like gentle moments in an eternal meditation, we find ourselves contemplating the most profound question of cosmic destiny: what lies ahead for our accelerating universe? The future stretches before us like an infinite ocean of possibility, where dark energy continues its patient work of expansion, gradually reshaping the very fabric of reality across dimenscales that dwarf human comprehension. As we drift deeper into this contemplation of cosmic tomorrow, we encounter scenarios that unfold with the slow majesty of geological processes, yet on scales that encompass the entire observable universe. The acceleration we observe today, this gentle but inexorable stretching of space-time, carries within it the seeds of transformations so vast and gradual that they inspire both wonder and a profound sense of cosmic peace. Consider first the scenario that physicists call the Big Rip, a possibility that emerges if dark energy proves to be what cosmologists term phantom dark energy. In this gentle catastrophe, the acceleration of expansion would itself accelerate, growing stronger with each passing eon. The process would unfold with cosmic patience, taking hundreds of billions of years to reach its crescendo. Galaxy clusters, those vast archipelagos of stars and gas that now drift slowly apart, would first lose their gravitational cohesion, their member galaxies scattered like seeds on cosmic winds. The imagery of this distant future carries a strange beauty in its inevitability. Individual galaxies, including our own Milky Way, would eventually succumb to the strengthening tide of expansion. Stars would be torn from their galactic homes, wandering alone through an increasingly empty cosmos. Even solar systems would not remain immune to this gentle dissolution, as the growing strength of dark energy would eventually overcome the gravitational bonds that hold planets in their orbits around their parent stars. Yet even in this scenario of cosmic dissolution, there remains something profoundly peaceful about the temescals involved. The process would unfold so slowly that countless generations of stars would live and die. Entire evolutionary epochs would pass, and the universe would continue its patient dance of creation and destruction for eons beyond our current ability to comprehend. The Big Rip, should it occur, would arrive not as a sudden catastrophe, but as the gentle conclusion of a cosmic symphony that has been playing for nearly 14 billion years. More likely, however, is the scenario that cosmologists call heat death, a fate that emerges from our current understanding of dark energy as a cosmological constant. In this future, the acceleration of expansion continues at its present rate, neither strengthening nor weakening, but maintaining its steady push that gradually separates all cosmic structures beyond the reach of their gravitational embrace. This heat death unfolds as a meditation on entropy and equilibrium, where the universe slowly approaches a state of maximum disorder and minimum energy density. The process begins with the gradual isolation of galaxy clusters as the expansion of space carries them beyond each other's gravitational influence. Within these isolated islands of matter, stellar evolution continues its ancient rhythm. But with each passing billion years, the raw materials for new star formation become increasingly scarce. The imagery of this far future carries a melancholic beauty. Red dwarf stars, those patient stellar embers that burn their nuclear fuel with miserly efficiency, would become the dominant lights in an increasingly dark cosmos. These stars, with lifetimes measured in trillions of years, would outlive their more massive cousins by factors that challenge human comprehension. They would shine like distant candles in cathedral darkness, their gentle light illuminating empty space where once great spiral galaxies turned in cosmic dance. As we contemplate these vast temescals, we encounter the patient evaporation of black holes through Hawking radiation, a process so slow that it makes the current age of the universe seem like a brief moment. A black hole with the mass of our sun would require more than 1067 years to evaporate completely, a number so large that it contains more zeros than there are atoms in the observable universe. Yet even these cosmic monuments to gravity's triumph would eventually surrender to the quantum fluctuations of empty space, releasing their accumulated mass energy back into the expanding void. The philosophical implications of these scenarios invite deep contemplation about the nature of existence and meaning in an accelerating universe. If the cosmos is indeed destined for heat, death, or dissolution, what significance can we find in our brief moment of cosmic consciousness? Yet perhaps the answer lies not in permanence, but in the very transience that makes each moment precious. In this far future, the cosmic microwave background would continue its patient cooling, its temperature dropping ever closer to absolute zero as the universe expands and ages. The gentle whisper of creation's afterglow would fade to an ever fainter murmur until it becomes indistinguishable from the quantum fluctuations of empty space itself. Yet even in this cooling, there remains something beautiful about the universe's gradual approach to perfect equilibrium. The mathematics of cosmic evolution paint these scenarios with equations that describe the slow dance of expansion and entropy. The scale factor of the universe continues its exponential growth, driven by the constant energy density of dark energy. Meanwhile, the density of matter and radiation continues its steady decline, diluted by the ever-increasing volume of space. These processes unfold with the inevitability of physical law, yet they carry within them a strange comfort in their predictability. As we drift toward sleep with these cosmic visions, we might find peace in the realization that our universe, whatever its ultimate fate, continues its patient expansion with the same gentle rhythm that has carried it through nearly 14 billion years of evolution. The acceleration we observe today connects us to the deepest mysteries of existence, reminding us that we are participants in a cosmic story whose ending remains beautifully uncertain, unfolding with the patient majesty of eternal time. In the deepest chambers of theoretical physics, where mathematics meets the fundamental nature of reality, dark energy presents us with perhaps the most profound mystery our species has ever encountered. Like a gentle whisper that reshapes the very fabric of existence, this invisible force challenges our most cherished understanding of the universe, inviting us into a contemplative journey through the foundations of physical law itself. The cosmological constant problem stands as one of the most humbling puzzles in all of science, a reminder that even our most sophisticated theories may be missing something essential about the nature of reality. When quantum field theory attempts to calculate the energy density of empty space, it produces a number so impossibly large that it would cause the universe to expand faster than light itself could travel. Yet observations revealed our energy's influence to be gentle, patient, accounting for roughly 68% of the universe's total energy density, with an almost whisper-quiet presence that has taken billions of years to become apparent. This extraordinary discrepancy between theory and observation spans 120 orders of magnitude, a gap so vast that it defies easy comprehension. Imagine trying to predict the width of North America and being off by a factor larger than the number of atoms in the observable universe. Such is the scale of our theoretical uncertainty, a cosmic reminder that the universe holds secrets we have barely begun to fathom. In response to this profound mystery, theoretical physicists have proposed alternative frameworks that gently reshape our understanding of gravity itself. Modified gravity theories, such as FR gravity, suggest that Einstein's equations might be incomplete descriptions of spacetime's behavior on cosmic scales. These theories propose that gravity itself might evolve, changing its character as the universe expands on ages, perhaps explaining the apparent acceleration without requiring a mysterious dark energy component. Extra-dimensional theories offer another contemplative pathway toward understanding, suggesting that our familiar three-dimensional space might be embedded within a higher dimensional reality. In these models, gravity might leak into additional dimensions at large scales, creating the illusion of accelerating expansion when viewed from our limited perspective. Like shadows on a cave wall, what we perceive as dark energy might be the projection of forces operating in realms beyond our direct observation. The coincidence problem adds another layer of mystery to our contemplation. Why does dark energy's influence become dominant precisely during the epoch when complex structures like galaxies, stars, and ultimately life itself have had time to develop? This cosmic timing seems almost too perfect to be mere chance, suggesting either extraordinary fine-tuning or perhaps indicating that dark energy and the evolution of cosmic structure are more intimately connected than we currently understand. Laboratory experiments now probe the vacuum of space itself, searching for subtle signatures of dark energy's influence on the smallest scales. These delicate measurements attempt to detect the gentle pressure of empty space, using laser interferometry and atomic clocks to sense changes in the fundamental constants of nature. Each experiment represents humanity's patient effort to understand the invisible scaffolding that shapes cosmic destiny. The search for dark energy extends beyond Earth-based laboratories to spaced observatories that map the universe's expansion history with unprecedented precision. Future missions will trace the subtle evolution of dark energy's influence across cosmic time, determining whether this mysterious force remains constant or changes as the universe ages. These observations will help distinguish between the cosmological constant and more dynamic forms of dark energy, potentially revealing whether the universe's accelerating expansion will continue forever or might someday reverse. String theory, our most ambitious attempt to unify all fundamental forces, offers speculative insights into dark energy's nature. In these theoretical frameworks, dark energy might emerge from the complex geometry of extra dimensions or from the dynamics of fundamental strings themselves. These ideas remain highly speculative, yet they demonstrate the profound implications that dark energy holds for our understanding of reality's deepest levels. The hierarchy problem, which questions why gravity is so much weaker than other fundamental forces, becomes intertwined with dark energy's mystery. Perhaps these seemingly separate puzzles are connected, with dark energy representing a manifestation of gravity's unusual weakness or the influence of forces that operate primarily in extra dimensions. As we contemplate these profound mysteries, we find ourselves at the threshold of potentially revolutionary discoveries. Dark energy's gentle influence on cosmic expansion might be the key that unlocks new physics, revealing aspects of reality that transcend our current understanding. The universe's patient acceleration becomes not just a cosmic phenomenon to observe, but a teacher guiding us toward deeper truths about existence itself. In this contemplation of fundamental mystery, we discover a strange comfort. The universe's deepest secrets remain hidden, ensuring that wonder and discovery will continue for generations to come. Dark energy's invisible presence reminds us that reality extends far beyond our current comprehension, inviting us to embrace both knowledge and mystery as we drift peacefully through the expanding cosmos, forever seeking to understand the gentle forces that shape our cosmic home. The eternal dance of expansion and wonder. As we reach the gentle end of our cosmic journey through the mysteries of dark energy and accelerating expansion, we find ourselves cradled in the vast, patient embrace of a universe that continues to unfold with serene inevitability. Like a cosmic lullaby that has been playing for 13 billion years, the gentle acceleration of space itself creates a rhythm so profound, so deeply woven into the fabric of reality, that it becomes the very heartbeat of existence. In the quiet darkness of your rest, imagine the universe as a vast, luminous ocean where distant islands of light, each one slowly, peacefully separating from its neighbors in the most gentle dance imaginable. Dark energy, that mysterious force comprising nearly 70% of everything that exists, works with infinite patience, stretching the very fabric of space-time with the tender persistence of dawn light, gradually illuminating the world. The supernova that first revealed this cosmic acceleration shine like ancient beacons across billions of years, their light carrying the profound message that our universe is not merely expanding, but doing so with ever-increasing grace. These stellar explosions occurring in galaxies so distant that their light began its journey when the universe was young, whisper to us across the cosmic dark about the fundamental nature of reality itself. Feel the peaceful rhythm of cosmic expansion, where each moment brings a subtle stretching of space, so gentle that it can only be detected by the most careful observations across vast scales of time and distance. This acceleration is not violent or dramatic, but rather like the slow, steady breathing of the cosmos itself, creating ever more space for galaxies to exist in peaceful isolation, each one a sanctuary of stars in the growing vastness. The cosmic microwave background, that ancient afterglow of creation, bathes the entire universe in the gentle warmth of its primordial light, now stretched by billions of years of expansion into the soothing embrace of microwave radiation. This light, older than the oldest stars, carries within its subtle fluctuations the seeds of all structure, all beauty, all the cosmic architecture. The dark energy now gently separates across ever greater distances. In the deep future that stretches ahead, like an infinite, peaceful dream, galaxies will slowly fade from each other's view, not through any catastrophe, but through the patient work of expanding space itself. Future astronomers, if they exist, will look out into night skies growing ever darker, ever more serene, as the universe enters its long, quiet phase of cosmic solitude. Yet in this eternal separation lies not loneliness, but profound peace. Each galaxy cluster becomes a perfect island universe, complete unto itself, carrying within its gravitational embrace all the matter and energy needed for countless eons of stellar birth, planetary formation, and perhaps even life itself. The acceleration ensures that these cosmic sanctuaries will remain forever pristine, forever protected from external influence. As you drift deeper into rest, let yourself become one with this cosmic perspective, feeling the gentle expansion of space itself as a soothing rhythm that rocks you into ever deeper peace. The dark energy that drives this expansion surrounds you, permeates you, connects you to the fundamental forces that shape reality on the largest scales imaginable. The mystery of dark energy remains beautifully unsolved, inviting us to rest in wonder rather than certainty, to find comfort in the unknown rather than anxiety in the unexplained. Like the gentle breathing of a sleeping cosmos, this force continues its patient work, creating ever more space for beauty, for contemplation, for the quiet unfolding of cosmic destiny. In the expanding universe, we find not emptiness but fullness, not separation but connection to something infinitely larger than ourselves. The acceleration of cosmic expansion becomes a meditation on impermanence and change, teaching us that even the grandest structures of reality are part of an ever-flowing, ever-changing dance of existence. Rest now in the gentle embrace of this expanding cosmos, feeling yourself supported by the same fundamental forces that guide galaxies across billions of light years. Let the patient rhythm of cosmic acceleration carry you into the deepest, most peaceful sleep, knowing that you are part of this grand, eternal dance of expansion and wonder, forever connected to the mysterious dark energy that shapes the very fabric of space and time itself. Sleep peacefully in the expanding universe, where every moment brings new space for dreams, new distances for wonder, and new depths of cosmic serenity to explore in the infinite darkness of rest.